Molecular polarity is something that kind of overshadows a lot of what we've been talking about with bonding. We have ionic bonds where electrons are transferred. Polarity really comes into play when we're talking about covalent bonding. What polarity is it's dependent upon how the electrons are shared. So in something that's a non-covalent or non-polar covalent bond, the electrons are shared equally by the nuclei. So if you're thinking of this in terms of, let's say, sharing a candy bar, what this is implying is both, if you're sharing it with another person, both people get equal pieces. So the electrons are spending equal amount of time with all of the atoms that are in the compound. Polar covalent bonds are unequal sharing of the electrons in the molecule. So what this results in is a charge separation in the bond. So not a full charge like an ionic bond, but it's called a partial charge. So you have a partial positive and a partial negative charge. We have a symbol that we use. It kind of looks like an incomplete 8. It's a lowercase gamma. So we have a partial positive and a partial negative charge. So this symbol helps us to denote the difference here between these partial charges and a full charge like we have in an ionic substance. This sharing, so equal sharing or unequal sharing, really comes back to electronegativity. So electronegativity is the ability of an atom in a molecule to attract shared electrons to itself in this case. So it's dependent upon the electronegativities, and you can actually do calculations for this type of bond. But for us, we're just going to take a look at it and in generalities. So we know from our last unit that fluorine is the most electronegative atom, while cesium is the lowest, or francium, depending upon the resource. What ends up happening in polar substances is we end up with a dipole moment, which is where the charge distribution is uneven, essentially. You can actually use an arrow to describe this. We're not going to really do that. This first image is kind of more of what I'm interested in us talking about. So if we're looking at water, which water, if you did not know, is a polar substance, water is very polar. So you end up with partial charges on your hydrogen, partial positive, and a partial negative on the oxygen. Why is the oxygen partially negative? Well, let's think back to electronegativity. On the periodic table, nitrogen, oxygen, and fluorine are the 3 most electronegative atoms on the periodic table, with fluorine being the max, which is 4. If you have one of those substances in a substance like water, it's going to be the negative side because of that large electronegativity, forcing, in this case, the hydrogen to be positive. If you think of the Lewis structure, we didn't draw it for water, but you would end up with lone pairs of electrons on the other side of the oxygen, which helps to indicate what's happening as well. So, for example, here with our water, you can kind of see using color the charge distribution. So water has a dipole moment. Carbon dioxide, which is the next example, does not have a dipole moment. The reason why is because of the symmetry of it. One of the easiest ways for us to determine the polarity is by looking at the symmetry. Water is not symmetrical. Water has these lone pairs of electrons, which we call lone pairs. Carbon dioxide doesn't have that. So while there are differences, they cancel each other out. So there's many ways that you can go about figuring out the polarity of something. So first off, if there's a lone pair on your central atom, it's going to be polar. So if we drew the Lewis structure of carbon dioxide, we have our central atom is our carbon. There's no lone pairs there. But something like water has lone pairs. So that's the first step. So right away with step A, I would be able to determine that water is polar and carbon dioxide is nonpolar, just looking at the symmetry. Or excuse me, looking at if there are lone pairs on the central atom. Symmetry is kind of the backup. If it is asymmetrical, it's going to be polar, and symmetrical is nonpolar. And I'm going to show you a few examples of this. So the first, we're going to have a few examples here to help explain this. So we're going to look at something that has lone pairs on the central atom. So something that represents lone pairs, let's not use carbon. Oops. Let's use nitrogen. We're going to have NH3 here. So the Lewis structure we drew in our Lewis structure section. We're going to have nitrogen with lone pairs on the top with the 3 hydrogen for ammonia. Because of the lone pairs, I'm going to highlight them for emphasis, but because of them, this results in a polar substance. No lone pairs on the central atom. Let's look at carbon tetrafluoride, which would be carbon with 4 fluorines on it. I think we did methane, and I think we did this as well. But here's your Lewis structure for it. There's no lone pairs on the central atom. When that occurs, you have to then look at the symmetry of it. So this is pretty much symmetrical. So it results in a nonpolar substance. Okay. So what do I mean by symmetrical versus asymmetrical? So I'm going to give you an example of this. So let's say we have let's use silicon. So we have 1 hydrogen and 4 fluorines. This represents an asymmetrical atom. So we have one side that's different. We have this hydrogen. Because hydrogen is going to share the electrons with silicon differently than the fluorine will, this results in a polar substance. So when we're talking about symmetry, this is the kind of thing we're talking about. Now, we're not going to be grouping right now into polar, slightly polar, slightly nonpolar, and nonpolar. We're just going to put everything into 2 groups for now. There are these kind of gray ones that are kind of fall in the middle, but for us, we're just 2 groups for right now. So this would be an example of an asymmetrical molecule. Another example of a symmetrical molecule, let's say we had a chlorine bonded with a chlorine. This is also another example of a symmetrical molecule resulting in a nonpolar bond. Okay. So right here is listing the specific shapes, which we're going to talk about later, which result in things that are either polar or nonpolar, and we'll come back to that. What I would like to do now is I'd like kind of to practice our Lewis structures and determine the polarity of these substances. So try this on your own and then unpause it to see the result. So I've already gone through and drawn the Lewis structures for each of the substances using the NAS method. So we're going to go through and talk about the polarity. So looking at NH3, NH3 has a lone pair on the top, meaning that this is a polar substance. If there's a lone pair on your central atom, right away it's going to be polar. So nitrogen, in this case, makes this substance polar. In the next one, I drew it 2 separate ways. Technically, the red is a little bit more correct, but for our purposes, either would be acceptable. If you go on to take AP Chem, you would have to draw the one in the red. We're not going to be real worried about it. But again, because we have these lone pairs of electrons, this also is a polar substance. So in the blue way, it kind of looks symmetrical, but the more important part is that you still have those lone pairs of electrons on the top, on the sulfur, because sulfur is your central atom, makes it polar. Next up, we have CF4. Notice there's no lone pairs on the central atom, and it's also symmetrical. So this is a non-polar substance. Okay, so it's perfectly acceptable to have lone pairs on your atoms you're bonded to. The one that you have to take time to really look at is the central atom. Next up, we have PCl3. We have a lone pair on the top of this one, so this would result in a polar substance. And the last one, again, just like the other one, sulfur, there's really two ways to draw it, but either way you have lone pairs, so this results in a polar substance. The last one we skipped because we did it earlier, but it would be nonpolar if you were looking at the polarity.